Hello, I'm Axel Dahmen, and I'd like to introduce to you my new concept of a new, more natural feeling way of doing interrupted or reverse transitions in CSS. Let's just dive into the details of my concept now. To begin with our considerations, we need to get a clear understanding of what an interrupted or reverse transition actually is. When do we actually speak of an interrupted or reverse transition? An interrupted transition or reverse transition basically consists of two non-complete transitions. Within the scope of interrupted transitions, it doesn't really matter whether the transition direction reverses or forwards. So far, so good. So what's wrong with the current specification then? To elaborate on this, let's start by having a look at the current situation. According to current specification, the adjoining transition, interrupts transition 1, yet it starts a second transition completely anew. You'd most naturally expect, though, the duration of the adjoining transition, to be dependent on the duration of the interrupted transition. Let's examine a reversed transition. I guess you'd expect the second transition to be significantly shorter when you've had cancelled the first transition right at its beginning than if you'd had cancelled the first transition right at its end. The same is true for interrupted transitions. I guess you'd expect a continued transition to a target point which is close to your current position to execute more quickly than a continued transition to a target point which is far away from your current position. Moreover, you'd expect a continued transition having a target position which is close to the original transition's target position to basically continue the original transition, having just a slight shift. See, the problem with the current specification is that with interrupted transitions, the adjoining transition actually stops the first transition and starts a second transition completely anew, which seems quite unnatural. A more natural approach instead would be if the second transition actually took the first transition's movement impulse, continue it to its new destination. That would seem more natural. Let's now have a look at the details of my proposal to see how this could be achieved. Let's start by examining a transition having a standard easing function applied. When transition 2 interrupts transition 1, we've already reached a certain property value and transition speed at this point. So the task now is to have transition 2 not start at this point of time, but instead we need to update transition 2 in a way that it appears to already have progressed and have the current property value and transition speed at this point of time. How do we achieve this? To achieve this, we need to correlate both transitions' speed at the point of time when the first transition gets interrupted. Using standard cubic easing functions, there are always two locations in a transition progress evaluating to the same speed. Any pair of equal transition speeds can always both be found in the acceleration and the deceleration phase of the transition. To determine whether we have to look in the acceleration phase or in the deceleration phase of the second transition to match the current transition speed of the first transition, we first need to calculate the average speed of the second transition. If the current transition speed of the first the interrupted transition, is slower than the average transition speed of the second, the adjoining transition, then we need to accelerate. So we need to look in the acceleration phase of the second transition to find a matching speed point. If, on the other hand, the current transition speed of the first, the interrupted transition, is faster than the average speed of the second, the adjoining transition, then we need to decelerate. So we have to look in the deceleration phase of the second transition for a matching speed point. Please note, if we'd be using inverse cubic transition easing functions, we'd also be required to reverse our search for the acceleration or deceleration phase. Because with these inverse cubic transition easing functions, acceleration actually takes place in the latter half and deceleration takes place in the first half. Using linear transitions, these considerations don't even apply, because linear transitions never change speed over time. So how do we get the second transition amended then? To achieve this, we now need to calculate a new starting value and starting speed for the second, the adjoining transition. For that it will have the current value and current speed now, while it's interrupting the first transition. In theory, we now need to go back in time. We need to know where would the second, the adjoining transition, have to have started to have the same value and speed that the current, the interrupted transition, has right now. We need to iterate through this calculation until we've found a hypothetical value and speed for the second adjoining transition that equals the current speed and value for the first, the interrupted transition. I've written a small piece of JavaScript code simulating the CSS transition suggestion, giving a proof of concept, and demonstrating a solution. It contains the algorithm I just mentioned. Let's have a look at it.
So this is my CSS transition simulation code. First, we got the transition class constructor here. It's initializing the easing function, so we don't have to calculate these values while the transition is in progress. Next, we've got the actual code that's performing the transition. This is the only main execution branch here. This is the branch that's being executed whenever a new transition, which is not interrupting a currently running transition, is started. If, however, a transition is started that would interrupt a currently running transition, the above branch would be executed instead. Here, first, the average or linear speed of the new transition is computed. Next, the current speed of the interrupted transition is computed. Here we convert time-related speed into movement-related speed, as we need to evaluate the true distance the value has changed since the last transition frame has elapsed. Given these values, we can now determine whether we need to accelerate or decelerate in order to match the new transition animation to the already running transition. If the current transition frame speed is slower than the desired new transition speed, then we need to have the new transition begin by accelerating in order to catch up. On the other hand, if the current transition frame speed is faster than the desired new transition speed, then we need to have the new transition slow down right from the beginning. The following calculation is an iterative process. So, well, it's not optimized, it's just a proof of concept. Here I'm computing the hypothetical starting point and transition speed to see if such altered transition would have already been fast enough to match and meet the current transition. As soon as the frame speed values match, we're going to use the computed hypothetical start value and starting time to initialize the new transition accordingly. Here we sham the new transition about the fact that it has already run to a certain amount of time and where it's supposed to have started. Given these fake values, the new transition state will now match the interrupted transition's position and speed. The deceleration branch is quite the same as the acceleration branch. The only difference here is the converse comparison, and that we are searching in the second half, the deceleration half of the Ising function. That's it.
Here you can find the sample code from my proposal. The result is amazing. You'll notice the most natural behavior on reverse transitions, interrupted transitions, and continued transitions. That's it. This has been my suggestion to an alternative CSS transition approach. I hope you enjoyed the video as much as I did, and I hope someone will find it useful and get it implemented into CSS.